Hello class, my name is Kafuma Henry and I'm going to be presenting a paper on deep ensemble learning and quantum machine learning approach for Alzheimer's disease detection. Alzheimer's disease is among the most chronic and neurodegenerative diseases that threaten global public health. The prevalence of Alzheimer's disease and consequently the increased risk of spread all over the world poses a vital threat to human safekeeping. So the paper addresses the challenge of early Alzheimer's disease detection using MRI scans, emphasizing the need for accurate and efficient classification models. Traditional deep learning approaches have improved disease classification but face limitations due to data scarcity and computational constraints. To enhance performance, the study proposes a hybrid learning and quantum machine learning approach, leveraging an ensemble of two ensemble models, that is VG G116 and ResNet 50, for feature extraction, and then quantum support vector machine for classification. So what is the computation problem? Like we've discussed, in this paper addresses the challenge of early detection and classification of Alzheimer's disease using MRI scans. The study aims to improve classification accuracy by combining deep learning models with quantum machine learning. Uh, um, AD Alzheimer's disease classification is treated as multi-class classification problem, categorizing MRI images in four classes, that is non-demented, very mild demented, and moderate demented. So the approach is to use two ensemble CNN models, that is VGG16 and ResNet 50. And then in the classification phase, a quantum vector machine is used to classify the extracted features from the two ensemble models. And the metrics used are accuracy, F1 score, precision, recall, and area under the curve. This study focuses on convolution neural networks, but as we know, under CNNs, there is use of multi-layer perception, which form the convolution networks. So in convolution networks, the CNN layers extract spatial features from MRI images, which are then processed by the QSVM. So these CNN models, like we've discussed, they are ensemble two models that are used to extract the features. So when these features are extracted, then they are concatenated together, and then they are fed into the quantum support vector machine for classification. The activation functions used in these two models, they use the ReLU activation in convolution layers to introduce a nonlinearity and improve feature learning. Then of course CNN uses biases in convolution layers to enhance feature learning. Proposed architecture, or the algorithm, the authors proposed sequential steps where two data sets, that is ADN1 and ADN2 data sets, are combined together, and then if we can move, this is the graphical representation. So we have uh, two uh, data sets which contain MRI images, and then they go through a pre-processing phase. In this phase, we do filtering and then cropping and augmentation of the images, the MRI images. So down here we have uh, two assemble models like we've been discussing. So on the left, that's where the VG G16 model, and then on the right, the Resonate 50. So these images from pre-processing phase are fed into these models, and the parameters for these models are configured to extract the features from images, and then the features that are extracted are concatenated here, and then the combined output from these assemble models is fed into the quantum support vector uh, model, support vector machine model for classification of these dementia images. Um, on the left side, we have the VG G16 model, and as you can see, if we can go to the previous slide, um, it has it consists of 9 convolutions. Then there are 2 batch normalization layers and 3 max pooling, 2 dropouts, then 1 batch normalization, and yeah, so multiple layers here that are used to extract the features. And then on the left other side is the resonate, and the features here, uh, whatever is extracted will be fed into the quantum support vector machine. So the QSVM model mm, uh, uh, does the classification, and then the output from this model is evaluated using the metrics that we discussed before, and that is the accuracy, the F1 score, and these ones are compared on the other traditional models to determine the performance of this model that has been developed. So, um, so the result from this model, according to authors, implied that this ensemble-based QSVM model is superior to other individual models in terms of performance, and as we are going to see, it uh, it does produce superior results in terms of the metrics that we've discussed. The activation functions that are used here, like we've said, ReLU, rectified linear unit, is used in convolution layers of the 2 ensemble models, that is the VGG16 and Resonate 50. And this ReLU function introduces nonlinearity. It also helps in avoiding vanishing gradient problems, and it also improves on the model efficiency by keeping only the positive activations. Then in the classification phase in the support vector machine, we have softmax, and this one converts logists into probability scores from out classification, from out class classification. The learning paradigms. This study employs supervised learning, and in the training data we have labeled MRI images from ADNI datasets, the ones we've discussed, which is ADNI 1 and ADNI 2 that are merged together. So under model training, we have an ensemble model, which is a combination of two CNN models, that VGG16 plus ResNet 50, and these are trained and tuned to extract the features from these MRI images. And these features from both models are concatenated together and then fed into a QSVM model, which learns from the labeled features, vectors to classify these AD stages. So what are the error correction and optimization strategies? So we have back propagation and gradient descent, and this is used in the two convolution network models to training and to minimize the classification loss. The optimization strategies are stochastic gradient descent. This is an optimizer with a learning rate of 0.0001 per step. Then batch optimization to stabilize the learning and speed up training. Then the dropout layers to reduce overfitting. Yeah, we showed this one in the illustration. Then we have the quantum kernel trick in the QSVM model, and this enhances classification by mapping data into high dimension quantum feature space. So in conclusion, this paper presents an innovative approach by integrating deep learning and quantum machine learning for Alzheimer's disease detection. The ensemble models of VGG16 and ResNet 50 extract deep features, while the QSVM enhances classification accuracy. The reported accuracy of 99.89% is impressive, but further validation in real-world clinical datasets and hardware feasibility for QSVM is still necessary, and this is an area for more research.